All right. Hello, everyone. Thanks for joining. I think we are all set in terms of the setup and the recording and everything. So I guess we might as well get started. So welcome to the first session of combinatorial and computational aspects of games. The first part of these discussions are going to focus more on the structural and combinatorial aspects. And in the second half, we will switch out to talking more about complexity aspects. So for the first part, I'm going to be closely following a book called Playing with Discrete Math. And we'll drop a link to this in the description of the video and also on the website. And today, we're just going to start off as warm-up, playing with a specific game, which we will use as sort of a running example to set up the sort of basic terminology, notation, ideas, and so on. And we'll dig a little bit deeper as we go along. So this game that we're going to be talking about is called the game of subtraction. And like many games that we will be talking about, it involves two players. And throughout, these players will often be referred to as the first and the second player, not surprisingly based on who gets the first turn, which brings me to the fact that it's a turn-based game as opposed to being a simultaneous game, which means that the first player goes first while the second player politely waits for their turn. And I will come to the fact that we sometimes have to, well, the first and the second are sort of universal in the sense that the first player is the player that goes first in the game, but sometimes we are talking about an intermediate snapshot of the game, in which case we will want to probably talk about the current player and the other player, because the person whose turn it is currently may be either the person who started the game or it may be the person who went second. So often, apart from first and second, we will often use the terminology of the current player and the other player, or as in the book, they call it the next player and the previous player, which I personally find to be slightly confusing because when the game starts, there isn't a previous player. So the previous player is really a way to talk about the player who is not playing the current turn. So we'll just have to keep that in mind. Most games have some rules based on which you play them. And then there is also what you might call a winning condition. You need to know ideally what you need to do to win the game so that you can strategize accordingly. And of course, some of these are loaded terms, things like strategy and who gets to win and so on do have formal definitions, but we'll see if we can hash those out, as I said, by example. So in the example of subtraction, the rules or the setup is basically the following. So to begin with, you have a certain number of tokens on the table. So I'm just going to say we have n tokens, although, okay, so unfortunately, it looks like I cannot write anymore because my stylus is out of battery. So I'm just going to speak for a couple of minutes while it recharges. So there are n tokens on the table, and the players are free to remove tokens from the table on their turn, but they can't just remove as many as they want. They have to remove either one token or two tokens or three tokens. They're free to remove 1, 2, or 3. And the game ends when there are no more tokens left to be removed. So if you happen to be the player who is stuck with no tokens left, then you lose the game. Okay, so the last player to move is the winner for subtraction. Of course, you are the boss, you make the rules. So you could also define a game where the last player to move loses the game. And that's the situation that you're trying to avoid. So that's a perfectly valid game as well. But for the most part, at least to begin with, we're going to be focusing on games where the player who has the last move is the player that wins the game. So you don't want to be in a situation where you're stuck without moves. So you can imagine that if the game begins with 1, 2, or 3 tokens, the first player has a clear strategy which is that they should just remove all the tokens immediately so that the second player is stuck. So if you have 3 tokens on the table and you remove 2, that would be a little bit unwise. And we assume that players are not unwise. We assume that they're going to play optimally, which means that, well, we also assume that they know how to figure out what's the best thing to do. And that's what they're going to do. Nobody is playing with a younger sibling that they're trying to help win and so on. That doesn't happen here. So when we talk about players winning, so if I say that from a particular starting point, the first player has a win, that's actually a shorthand for saying that the first player has a way to make their moves so that no matter how the second player responds to their moves on each turn, they always can ensure that they end up winning the game. So that's what is called a strategy. So you can basically map out a plan so that you begin by doing something and the second player or the other player does something in response. And then you can always respond to that response in a way that will always keep you in good stead, so to speak. So this will all become clearer as we walk through examples. But the idea of saying that the first player wins, well, of course, I mean, technically, you can always even lose a game of tic-tac-toe. And like I said, even in subtraction, if you have 2 tokens on the table and you remove 1 as the first player, then, well, you lose. So although it's possible for the first player to lose, we are going to assume that these things never happen. So we're always going to talk about the first player wins if there are 1, 2, or 3 tokens. You might say that doesn't sound technically right, but what we really mean is that if the first player is playing optimally, then they have a way to win from these positions. So, but that's a mouthful of words to say every time, so I won't be saying that every time. I'll just say things like the first player can win from here, the second player can win from here, and so on. So they take that with a pinch of salt and just autocomplete it to the longer sentence in your head for what it actually means. So let's hope that this works now. So we have n tokens to begin with. And the moves, if you like, involve removing 1, 2, or 3 tokens on your turn. And the game ends when you have 0 tokens left. And the last player to move wins the game. So that's the entire description of the game. That's what's going on here. And like we said, we've already sorted out a simple scenario where we have said that, okay, if n is 1, 2, or 3, then it's a first player win. What about if n equals 4? Is somebody want to suggest maybe in the chat who wins if there are 4 tokens on the table? Well, whoever is playing with 4 tokens to begin with, what are the moves that they have? Well, they can remove 1, 2, or 3 tokens. So the possible games that they can go to are games with 3, 2, or 1 token. So if you choose to remove 1, you're left with 3. If you choose to remove 2, you're left with 2. And if you choose to remove 1, you're left with 3. In all of these scenarios, unfortunately, the other player can take the game away because of what we just saw above. So, so as has been pointed out, this is a second player win. Just by case analysis. Don't really have a choice. Now, what if there are 5 tokens on the table? I'm just building this up a little bit slowly, but we'll try to hopefully develop this so that we have a more general way of looking at the whole picture in just a moment. But what can the first player do if they have 5 tokens on the table? How many tokens would they want to remove, you think? But clearly, you don't want to remove 2 or more tokens, because if you remove 2 or more tokens, you're in a situation where you're throwing the game away. And we don't do that sort of match fixing here. So your best bet is to actually remove just 1 token, as has been pointed out. And so that's going to be a first player win. What about if there are 6 tokens on the table? Well, in this case, again, remember that if we give the other player a situation where they have 4 tokens, then from there, it's the other player that wins. So I hope that makes sense. So if you have a certain number of tokens and you can go to a situation where you have only 4 tokens left, the person who is playing with 4 tokens is not the person who wins, right? It's the other player who wins from 4 tokens, right? That's the second player win. So you want to create that situation for your opponent. So from 6 tokens, you should be removing 2 so that you're left with 4. And then the other person is stuck. No matter what they remove, it's going to come back to you for a win. So a similar argument works when you have 7 tokens as well. You can remove, in this case, 3 tokens to go to the place where the other player wins. And I realize that this may be confusing because, when you give the game to the other person, then from now on, you are the other player. So if the other player wins, that's good for you. So to make this just a little bit clearer, what we normally do is actually try to visualize the possible scenarios that we are going to get into using something called a game tree, which is a fairly natural concept. So let's start with maybe an example that involves, say, 8 tokens on the table. So that's the number of tokens that we start with. In general, you can do this for any n, but just because I want to draw a concrete game tree to illustrate the concept, I'm going to start with 8. So from 8 tokens, there are 3 possible scenarios that you can get into. If you were to remove 1 token, then you're left with 7. If you remove 2 tokens, then you're left with 6. And if you remove 3, then you're left with 5. Let's dig a little bit deeper into what happens when you have 5 tokens left on the table. From here, again, if you remove 1 token, you're left with 4. If you remove 2, left with 3. And if you remove 3, you're left with 2. Now, once you have 3 and 2 tokens on the table, we know that it's almost game over. But just for the sake of drawing out what the possibilities are, from 2 tokens, if you remove 2, you end up with 0 tokens. If you remove 1, you're left with 1 token. And from here, there's only 1 move possible, which is 0. From 3, you can be left with 2, 1, or 0, depending on how many you remove. From 1, it's a 0. From 2, it's 1 followed by a 0 or a 0. So we actually already have the tree for 2, and you've probably noticed already that this thing here and this thing here are exactly the same. So going forward, if I know that I've drawn something out before because I'm quickly going to start running out of space, I'm probably not going to redraw the trees once we know that we have them, because you can cross-refer them in the other corner of the diagram. So from 4, you can be left with 3, 2, or 1, depending on how many tokens you remove, and we've drawn out all of those game trees, so we know what's going on. From 6, you can be left with 5, 4, or 3 tokens, based on how many you remove. And from 7, you could be left with 6, 5, or 4, depending on how many you remove. And all of those trees are well understood. I don't know if I can try this stunt here of pasting this game tree. This is probably going to look weird for a bit, but okay. So this is the game tree for 5 that we just worked out, and you can probably imagine that the rest of it pans out nicely as well. Now, why is this game tree useful? It's because it gives us a lot of information about the players who win. So let me actually momentarily get rid of the crowding on the page. Okay, did my screen share just drop, or is it still on? I don't see it on my screen anymore. Okay, now I do. So hopefully it's all right. Yeah, thanks. Okay, perfect. So, so what can we say about who is winning and who is losing? This is the point where it's useful to think of it in terms of the current player and the other player. So at any node in the game tree, I'm going to label it as green if the player who is playing at that position has a win. And I'm going to label it red if the other player has a win, which is to say that the player whose turn it's currently not has a win. So at the bottom of the game tree, we have these nodes that are labeled 0, which means we're in this awkward situation where we have started the game with no tokens on the table. As you can imagine, this is a little bit unfair for the first player because they just don't have any move straight off the bat. So in this case, hopefully it's clear that the current player loses because they have nothing to do. So they trivially lose the game. And that's equivalent to saying that the other player wins. However, what does this say about everything that leads up to a node like this? So this is where we can see that if you have a 1, then it's a win for the current player because they can direct the game to a situation where the current player loses. And once the turns have switched, the other player is the current player, right? So the player who is faced with 1 is actually going to win their turn because they can take the game to a situation where whoever is playing from there is going to lose the game, right? So what happens at 2? At 2, there are 2 possible moves. One of them takes you to the grave, but the other one takes you to victory. So the point is that because you are in control, you can take the game. Well, remember, you should take the game to the grave because you're now thinking about what's going to happen when the other player takes it from here. So because, so maybe it was a bit confusing when I said that you have an option where you can take the game to victory. So this option is actually the bad one for you because it lets the other player win. This is the one that will work out nicely for you because it forces the other player to lose. So from wherever you're standing in the game tree, if you can see that you can go to a red node, then you're happy and you can label the current node green because that means that you have a choice which is good from your point of view. So that gives us, well, I forgot to mark the other one, but yeah, so this is the situation we are in. The 3 and 2 are also good for us, and this we had already observed earlier. What can we say about 4? Well, notice that from 4, everything is victory for the other player, which means that you're going to be a little bit stuck at this position. So no matter what you do, you're going to go to a universe that's a win for the player who plays from there. And so you have to offer up victory to your opponent. So from 4, there is no hope. But from 5, there is, because from 5, you can go to 4. So a defeat in this round implies a win at a higher position. And so for so 5 is good for us, 3 is good for us, 4 is bad for us, but because 4 is bad for us, 6 is good for us. So from 6, we can go to 4 and stump the other player. And same is true for, well, let's see. Same is true for 7. Because 4 is bad for us and is accessible from 7. 7 is good for us because we can push the other player into that bad situation. But now what can we say about 8? From 8, it's greens all the way, which means the situation for you is good or bad. The situation for us is indeed bad because there is no way that we can win from here based on the fact that whatever move we make is going to be winning for the other player. So hopefully that's clear. And that gives us the general definition of a game tree. So the nodes of the game tree are positions in the game. All the possible positions of the game. So you start out at the root. So the root corresponds to the starting point. And in general, from any node, you have as many children as there are valid moves. And those describe the scenario that the game is going to be in if that move was executed. And we're going to label each node as a win or a loss for the player who is currently in that position. So this is a current player win. And this is a other player win. And notice that because of the way these games are set up, the other player win corresponds to a current player loss as well. And the rule is going to be, as we have seen, if you are at a node where all the children are current player wins, then the current node is a other player win. Does that make sense? Because from here, wherever you go, that player is going to win. And so you have nowhere nice to go. But on the other hand, if you have at least one child in the tree that's other player win, then the root is a current player win. Okay. So that completely determines what's going on in such games, right? And in fact, when you're drawing out the game tree, if you want to be lazy, when you're at a particular node and you're traversing its children, so typically when you want to label these nodes as green or red, you typically start from the leaves. And remember, we said that when you have no more moves left, then you lose, right? So the leaves are always current player losses or other player wins, right? The leaves are by definition places, well, leaves in a tree have no children. So these are places in the game from where you can't go anywhere else, so that you have no moves left, right? So, so the leaves are where you're stuck. And so the leaves always start out as being other player wins. And now you climb your way up the tree and you update the labels according to the following rule, the rule that we just discussed here. So the laziness that I was talking about was that suppose you're populating or you're trying to figure out what sort of a node this is and you're traversing its children. And at some point you happen to see that you have encountered an other player win, then you already know, even without looking at the rest of the children, that this is a current player win, because you can, yes. I hope I didn't, I tend to get these things mixed up a little bit. I hope I said that right. So yeah, because you can send, you can execute this move, and the bad situation is now with your opponent. So that was the logic. And now the point is that you don't even care what these other children look like. However, of course, if you don't see a red node at all, you have to chug your way all the way up to the end until you have actually evaluated all your children. And at that point, if you have only seen greens, then you know that the current node has to be a green. However, for the red nodes, sometimes you may be lucky and you can, especially if you were writing a program to update the colors of the game tree, sometimes you can just choose to not evaluate or look at the rest of the children if you have seen a red child somewhere on the way. So I think in the book, they call this trimming the game tree. They're not literally trimming the tree, but you're just trying to avoid redundancies where you can. So we already did a little bit of trimming when we were drawing the game tree. So if you have already seen positions before, then you don't need to draw them out again. You can just refer to the place where you have worked it all out, right? So that's one kind of trimming. And the other kind of trimming is not a physical trimming of the tree, but it's just that when you are going through the nodes to figure out how you should color the nodes, sometimes you don't need to go through all your children if you happen to be lucky and you find a red node early on in life. Yes. So that's pretty much what I wanted to talk about in terms of setting up notation and the concept of a game tree, which is inherently recursive. You can imagine that this is a very general concept that applies well beyond subtraction. It applies to any game where you understand the moves, the rules are well defined, and you can play around already with subtraction. So with n tokens, we said the moves are 1, 2, and 3, but the moves could have also been 127 and 350, or it could be any three numbers that you like. Of course, if you don't have a 1, your game may not go down to 0. It may truncate even sooner because you don't have valid moves already at other numbers, right? So for example, if your numbers happen to be 7, 8, and 9, then already if you have 6 or less tokens in the table, all of those are leaves in the tree because there's nothing you can do from there. So you've probably guessed already is that subtraction with 1, 2, and 3 is a first player win if and only if the number of tokens is not 0 mod 4. You've probably sensed this pattern as we were going along. We had skips of 3 essentially. So 1, 2, or 3 is good for you, 4 is bad, 5, 6, or 7 is good for you, 8 is bad, 9, 10, 11 is good for you because you can piggyback to 8, but 12 is bad because all the previous 3 moves are good for the other player, and so on. So good for the current player, sorry. So you've probably discovered this pattern already. What would be nice food for thought is, can you generalize this to other sets of numbers? You work through the game trees, perhaps, for some other combination of numbers that you like. And I guess that's the only food for thought I have for now. So this would be a good time to stop. We are also on time, I think. We will continue tomorrow with ways of combining games and other interesting things. So thanks, and that's it.